Hello, welcome to this class. Today we will talk about very important technique called as a photolithography. Alright. The photolithography comes from the Greek word photos and lithos. So, the carving from a single stone, that what is means is carving from a single stone. Now, what we will be looking at and we will focus on would be on ultraviolet photolithography or UV photolithography. Okay. There are different kind of lithography techniques: X-ray lithography, electron beam lithography, UV lithography. We will talk about UV lithography in this particular class. Now, before we understand lithography, we should understand a few things. One, a term called photoresist. Alright. So, let us see the slide. Okay. So, what I said, we should learn lithography, and in lithography we should understand certain terms. The first term is photoresist. Photoresist are of two types: positive photoresist and negative photoresist. Alright, positive photoresist and negative photoresist. Now, we should also understand another term called masks. Alright, mask again are of two type: bright field mask and dark field mask. Okay. Photoresist two types: positive, negative. Mask two types: bright field, dark field. Okay. Easy. Now, let us understand the properties of this photoresist. Okay. So, if I use, let us say if this is the mask and let us draw plus. Okay. If I use a positive photoresist, this is a mask. If I use positive photoresist, then what I will have is the same pattern that was there on the mask. But if I use negative photoresist, then what will I have? I am not just drawing completely, like I am just understand that whatever I have here, this pattern that you see, right, is all dark. This is all dark. Okay. In a way, what we understand is that whatever the pattern that was there on the mask, same pattern comes on the wafer if I am going to use positive photoresist, and whatever the pattern is there on the mask, opposite of that will come on the wafer if I am going to use negative photoresist. Easy. Same pattern positive photoresist, opposite pattern negative photoresist. You see here. So, wherever the in another, if you read different books, then different books different things, it is written in a different ways, meaning is same. In some books you will read that the area for positive photoresist, the area which is exposed becomes weaker, right. For positive photoresist, the area which is exposed through the mask, right. How we are exposing mask? Through ultraviolet light. So, the area which is exposed to the ultraviolet light, the wafer have a spin coating of photoresist, and then on this spin coating of photoresist we load the mask. When we load the mask, we expose it through the ultraviolet light, and the area which is exposed becomes weaker when we talk about positive photoresist. The area which is not exposed becomes stronger. We can see here from this particular example, this is example of a positive photoresist. In case of negative photoresist, the area which is exposed becomes stronger, the area which is not exposed becomes weaker. This is the case of negative photoresist, right. Easy. Now, let us see the mask. I will show you the mask, right. So, let me wear the gloves and then I will show you the mask, how mask looks like, bright field mask and dark field mask. Since the material that we have been using is chrome, so we call this as a chrome mask as well, alright. Since material we are using is a chrome, we call it a chrome mask. So, first let me show you the bright field mask. Okay, can you see on my in my hand, right. This is the bright field mask. The field is bright, right, and the pattern is dark. Now, we can see, right. See, there are certain patterns in this particular field here, but you can see my face through that, right. That means the field is bright and the pattern that is there here, right, it is dark. This is your bright field mask, and what is the size of this mask is a 5-inch mask. How can I say it is a 5-inch mask? Because I will show you the wafer, okay, and how we load the wafer also. So, it becomes easier for you to understand. Okay. Now, this is not a right way to hold the wafer, but just for you to show, this is a 4-inch wafer, this is a 5-inch mask. You have to load the wafer. So, there is a mask aligner, okay, which is used as a lithography system. So, once you load the wafer, it looks like this, okay. There is a wafer now loaded onto this particular mask, right, is a 5-inch mask. So, on the back side you can see, if I just put it back side, this is a wafer here, right. So, the wafer will get exposed through the mask, right, the light will get pass through the mask. Now, the area which is transparent, light will pass through it. There are area which is not transparent, light will not pass through it. This is 5-inch mask, 4-inch wafer, double side silicon wafer. The way to hold the wafer is by using a tweezer, right, by using a tweezer. Now, this is your bright field mask. So, how the dark field mask looks like? Let us see how dark field mask looks like. So, now we will see the dark field mask. Okay. Can you see the dark field mask, right? Most of the field is dark, only some area is transparent, most of the area is dark. This is also a 5-inch mask, chrome mask, 5-inch mask, chrome mask. It is a dark field mask, okay. Got it? Yeah. 5-inch mask, alright. So, dark field mask. Now, bright field mask you have seen, dark field mask you have seen, silicon wafer you have seen, thermal oxidation you have seen. So, now let us perform a lithography step, okay, and through lithography step you will see how to pattern, pattern what? Pattern different material, so to form devices. See, this is a tweezer, this is tweezer with which we hold the wafer, alright. Tweezer is used to hold the wafer. This is one kind of tweezer, this is another kind of tweezer, right. This is another kind of tweezer, right. So, tweezers are used to hold the wafer, all right. So, now let us see the screen and let us see the steps, all right, for photolithography. So, please let us read. The purpose of photolithography is to print features on a wafer directly or by using photoresist. Generally, features on the top surface of any sample are patterned using photoresist by exposing to UV light, development and etching of the target layer. So, for the first step that we will use is cleaning of the wafer, right. Once you clean the wafer, this cleaning of wafer is called RCA 1 and RCA 2 cleaning, okay, RCA 1, RCA 2 cleaning. RCA 1 stands for Radio Corporation of America. Now after wafer cleaning we go for pre-bake and primer coating. Pre-bake and primer coating. So pre-bake is used to evaporate any moisture, okay, because when you clean the wafer and you rinse it with DI water, deionized water, you rinse the wafer with deionized water, then you need to dry the wafer, but still there will be moisture, and to remove the moisture we go for pre-bake. Pre-bake is about 150 degrees centigrade. After that you coat it with primer. So coat what? Coat the wafer with primer. Now why primer coating is required? To improve the adhesion of photoresist. So this primer coating is done to improve the adhesion of photoresist. Not every time in lithography step we require primer coating, okay. So that is, you need to also learn that. The next step is you coat the photoresist. So photoresist spin coating. Spin coating is done initially at a lower RPM. So initially at a lower rotations per minute, and then let us about 500 RPM, followed by increase in the rotations per minute about 2000 to 3000 rotations per minute, okay. So initially we can use the lower RPM, so to have a uniform deposition, followed by increasing this rotations per minute, so that we can have a thickness of the photoresist as desired, alright. So we can have thickness of photoresist anywhere from 1 micron all the way to 3 micrometer and so on. If there is a thicker photoresist, there are thicker photoresist as well, whose viscosity is high, then we can have approximately 5 micrometer as well, okay. But in case of SU8, which is another photoresist, we can increase the thickness all the way to 200 micrometers as well, okay. So let us not worry about SU8 for now. Let us understand that by using the spin coating you can change the thickness of the photoresist material, okay. So now once you perform the soft bake, so after photoresist spin coating you have to perform the baking. That baking is done at a 90 degree centigrade 1 minute on hot plate. This is called soft bake, or we also call as a pre-exposure bake, soft bake or pre-exposure bake. After pre-exposure bake we go for alignment and exposure. Alignment and exposure, I just have shown it to you how to take a wafer and how we can use a mask, align it. Alignment and exposure is also there in the lab video. So it will be easier for you to understand it better, but for now let us have a vision, right, or let us visually understand, right, or at least let us think about it, that if you have a mask, right, and if you have a wafer, how to align this wafer with the mask. So I will again show you the mask. If you can just see me here, see, suppose this is the mask, right, and that is why I said let us visually understand. So because we can see and then we can think about how it may be. But now this is what I am holding right now, but it is loaded like this, because in the mask aligner the UV is here, right, wafer is here. So we have to align the sorry, you have to align the wafer. You can align the wafer by moving in x direction, moving in y direction, or rotating in theta. So rotation is in theta, right. So by aligning the wafer and a mask, then you will expose it. So alignment and exposure is done only after soft bake is done, right. So let us go back to the screen, and what we see is wafer clean, pre-bake, photoresist spin coating, soft bake, alignment and exposure. After alignment and exposure, the next thing is development. What is development? We have to, after exposure is done, that means I told you that depending on the positive or negative photoresist, either the area which is exposed will get developed, or the area which is exposed will get strong, depending on what kind of photoresist you use. So that for development is photoresist development. So suppose you have positive photoresist, the same pattern of the mask will come on the wafer, other area will get developed. Once you do that, you have to perform hard bake. Hard bake is done at 120 degree centigrade for 1 minute on hot plate, again depending on the data sheet. This is done at 90 degree centigrade for 1 minute, this is done at 120 degree centigrade for 1 minute. This is all assuming that we are using hot plate. Finally, you can inspect the pattern, alright. So, these are the steps for lithography. Let us go to the next slide. So, as I told you, the first step is wafer cleaning and pre-bake, and you can see that the wafer cleaning methods can be bubble jet, high pressure rinse, further followed by sonication, and the dehydration bake or pre-bake is used to remove the moisture after wafer cleaning process. The primer is used to improve the adhesion of the photoresist. The primer is HMDS or hexamethyl disilicon. After coating the primer, you have to heat it at the wafer at 200 degree centigrade to 250 degree centigrade for about 1 minute. Here you can see that after the resist is coated and the wafer is aligned and exposed, right. If it is a positive photoresist, then the same pattern which is there on the mask, right, will get repeated onto the wafer, right. The area which is not exposed will get stronger in another way, or the area which is exposed will get weaker. That is also true for the positive photoresist. So, let us not get confused with that. Just assume that whatever the pattern is there on the mask, same thing you will get on the wafer. Not assume that, it is a fact. So, whatever the pattern is there on the mask, the same pattern will come on the wafer, alright. Now, let us go to the next slide. So, what is photoresist? Photoresist is a solid organic material. It is used to transfer the pattern to the wafer surface. It changes its photosolubility due to photochemical reaction when exposed to UV light. It should have a high H resistor and good adhesion. What does that mean? So, suppose I have a photoresist and let us say I have this silicon wafer, oxidized silicon wafer, right. So, we have oxidized silicon wafer here, and on that oxidized silicon wafer we have let us say aluminum. Now, I perform photolithography and my photoresist is here, alright. This is my photoresist. This is aluminum. Alright. Now, after this is photoresist that we have a pattern after performing the photolithography process. That means, we have spin coated the photoresist, perform soft bake, align with the mask, expose it, develop it, perform hard bake, and then we inspect it, and the photoresist is properly patterned. Now, if I dip this wafer in aluminum etchant, what should happen? That aluminum should get etched, aluminum should get etched from all the area except the area which is protected by the photoresist, except the area which is protected by the photoresist. So, this is what we are expecting, right. But if the H resistance of this positive photoresist is poor, then it will not withstand the aluminum etchant and we will not be able to get this particular pattern. That is what H resistance means. It should have a good resistance against the etching or the material which we are the chemical that we are using to etch the material, alright. So, how to coat the photoresist? Initially dispense 3 to 5 ml of photoresist, perform slow spin followed by ramping up at 1100 degree centigrade to 5000 rpm, it spreads by centrifugal force, and the quality measures are time, thickness, speed, uniformity. There are two types of photoresist, negative and positive. There are two types of mask, bright field and dark field, and you can see that if I have a bright field mask and if I have positive photoresist, same pattern is there on my wafer. If I have bright field mask and I use negative photoresist, opposite of whatever the pattern that was there on the mask will come onto the wafer. The same thing is illustrated in this particular figure as well. So, this is how the photoresist is dispensed. There is a vacuum pump, there is a spindle, vacuum chuck. So, the wafer is holded on to this vacuum chuck, otherwise if there is no vacuum, wafer will fly, right. So, the wafer is holded with the help of vacuum chuck, the spindle will spin the wafer, and initially we have to dispense the photoresist using photoresist dispenser. You perform slow spin so that uniform coating occurs, and then change depending on change the speed depending on thickness that you want as for a final photoresist. As you can see that how the thickness versus spin speed is related, that if you increase the spin speed, the thickness will decrease. If you decrease the spin speed, the thickness will increase. If you increase the time of rotation, the thickness will decrease. If you decrease the time of rotation, the thickness will increase, right. And in other way, thickness is inversely proportional to the under root of spin speed. Then we can also understand that there are different kind of photoresist, viscous, less viscous, high viscous, and so on. So, depends on what kind of photoresist you use. You need to also look at the HMDS. You should also look at the data sheet of each photoresist, and the soft bake and high bake temperature mentioned, and also the process time mentioned in the data sheet. Now, what is the role of soft bake, right. So, the role of soft bake is to improve adhesion, improve uniformity, improve etch resistance, optimize light absorbance, and it is one of the characteristics of the photoresist. So, when you expose the photoresist, you can cool the photoresist with the help of cool the wafer to the room temperature before you expose the UV light, right. So, why? Because after you perform the soft bake, which is at about 90 degrees centigrade for 1 minute, you let the wafer cool down and then you expose it. Now, the details about how the lithography optics works, right, we have already covered in the TA class. So, you will see in detail. But for just understanding, the light will pass through the mask, and it is very important to understand how much should be the distance between the mask and the lens through which the light will pass through, and the reflected light is collected by the lens, and the ideal light intensity should be like this, but the practical one you will get something around this particular waveform. You can also understand that depending on the types of the material, your dosage of the exposure would change. So, you need to optimize the process parameter. When you develop the photoresist, that means after exposure you unload the mask and you dip the wafer into a photoresist developer, then you can see that if there is normal development, you will get a very good feature size. If there is an incomplete development, the photoresist will stay. If there is a under development, then you can see here, while if there is a over development, means you can if you dip the wafer and forget to take it out, then the extra area will start etching, which we do not require. So, always understand that the best way is to follow the process time and recipe, all right, process time and recipe, you would always follow these things. Example, negative positive photoresist. If this is a mask, right, if you are using negative photoresist, then you can see that whatever the pattern that was on the mask, right, it will not be there on the photoresist, and if it is a positive photoresist, whatever the pattern is there on the mask will be there on the substrate or on the photoresist. In another way, again, the area for the negative photoresist, okay, for the negative photoresist, the area which is exposed will get stronger, the area which is not exposed will get weaker. For positive photoresist, the area which is exposed will get weaker, the area which is not exposed will get stronger. Okay. So, there are some basics of mask. You can use the Clevin software to design the mask. You can also use AutoCAD. The mask material can be of glass plate with chromium coated, sometimes it is also called as a chrome mask. An electron beam is selectively used to pattern the mask, develop the resist and remove chrome from the desired area to form the mask. This is a mask making process. You should also understand that the mask should be defect free completely, otherwise it will affect the devices or chips. Now there are certain alignment and test structures, and we will take the example of this alignment test structure in next class, where we will take a lithography and we will perform a two-step process so to fabricate a device, and in that you will see that how the alignment marks which are here, this kind of alignment marks are there, right, are useful for aligning the wafer with the second mask and third mask and subsequent masks. We can also use Fe2O3 on soda lime glass. So this is one kind of mask, chrome mask is second kind of mask. Bright field is transparent, most of the field is transparent, dark field most of the field is darker in nature. Now what are the defects in photo mask, right? So there are several kind of defects. The first one is chrome spot, second one is chrome extension, next one is chrome bridging, next one is clear break, next one is pinhole, next one is clear extension. All this kind of defects in photo mask causes the the device performance to degrade. For example, if you have device with a hole, then let us say you just take an example of a resistor, right? A resistor is given by rho L by A. Now whatever resistance which is given in ohms. So suppose you have measured whatever the resistance depending on the length and area, if there is a hole like this which is a pinhole, then the value that you have measured and value that comes will be different. If there is extension, there is a difference. If there is a break, it is a open circuit. If there is a short, it is a short circuit. If there is a chrome extension like this, again there is a problem, right. So everything is a problem. If there is a chrome spot like this, now you say that this is outside the mask, how does it matter? No, this is fine when we talk about the resistor, but when we talk about a chip, right, then in a single silicon die you have millions of transistors. In this case, whatever here triangle that you see within this circle, right, that will cause millions of transistors to fail in a process, and that is why it is not correct. Defects in the photo mask are not allowed. The lithographic process, you start with the wafer, coat the photoresist, pre-bake it, align with the mask, then expose it with the UV light, then you perform the post exposure bake, develop, and then you can look at the patterns. So the image of the lithography if you want to further understand is nothing but a image of mask is projected onto photoresist coated with surface. This optical photolithography system includes. So now the mask aligner, right, or what the mask aligner will include. So one is the design and operation of exposure tool. Second is optimization of the chemical process that occurs once the photoresist is exposed. Light source may be either visible, ultraviolet, deep ultraviolet or extreme ultraviolet light to generate the image of the mask onto the wafer. Now there are three primary measures of the performance of a lithography system. The first one is the resolution, how good resolution you can get, what is the minimum feature size that you can get, and it depends on photoresist to reconstruct the pattern from the aerial image. The sensitivity of the photoresist material is important, and finally the alignment system, how well your alignment mask aligner system is there will also determine how good your device is or what is yield of your devices with a lot of accuracy and less failure. To decrease the feature size, a source with a shorter wavelength can be used. So generally UV lithography we get about 2 microns feature size, but if you go for electron beam lithography, then you can have a lower feature size because of the shorter wavelength. There are different kind of sources, for example G line source, I line source, KRF laser, ARF laser and so on. So when you talk about lithography system or exposure system, then there are three different kind of printing. The first one is called contact printing, where we will have the mask in contact with the wafer, as I have been showing it to you that the mask and wafer are in physical contact. Second one is proximity printing, it is at proximity with respect to the mask, and third one is a projection printing. Let us see one by one. So, in the contact printing, the mask is placed chrome side down in direct contact with the photoresist layer on the mask, as you can see from this particular image, right. This is a contact printing. Contact printing systems are capable of high resolution printing because the mask is in contact. These systems are not efficient for printing very small feature size, and also it cannot be used for high volume manufacturing, because every time you have to align, you have to have a contact, physical contact, and then you have to expose. So, it cannot be used for the high volume manufacturing. But the hard contact between the mask and the resist on the layer may damage the or contaminate the mask. So, these are the advantage limitation. Advantages that you can have a better resolution, disadvantages cannot be used for high volume manufacturing and can contaminate the mask. Let us go for the second one, which is your proximity printing. So, let us go to the next slide. So, proximity printing largely solves the problem of contaminating mask by avoiding direct contact. You can see here there is very small gap between the mask and the wafer. Now, because of the separation of wafer and mask, the resolution may be degraded. Practically minimum feature size of 20 micron can be achieved. The resolution of this system improves as the exposure wavelength decreases. For example, for X-ray the wavelength is about 1 to 2 nanometer, then we can have a better resolution. Both contact and proximity printing requires 1x mask, which are difficult to produce for reduction system. Now, let us see the third one, which is the projection printing. So, the most widely method of exposing wafer in lithography is the projection printing. This system provide high resolution, but without contaminating the mask. Why? Because there is no contact between mask and the wafer. In the projection exposure tool, the mask is physically separated, as you can see here. The mask is somewhere here, the wafer is somewhere here, right, and the because of this the contamination issues are not there. Generally, optical system reduces the image 4x or 5x, which means that only small portion of the wafer is printed during each exposure, but there are steppers to expose the complete wafer. All right. Now, if you want to further improve the resolution, you can use electron beam lithography, in which there is a electron gun. As you can see, there is a alignment coil, and then there is a front condenser lens of blanking plates, followed by second condenser lens, followed by limiting aperture, final lens, and then the electron we have a photoresist substrate and the mechanical state. So, electron will scan over this particular substrate, and while it is scanning it will also expose it. So, the size limitation in optical lithography arises because of the resolution depends on the wavelength of the light. As electron beam has much smaller wavelength, it can achieve much higher resolution. Image lithography, very narrow electron beam is used to scan and write the directly on the wafer. This is a direct writing method. This step consists of electron source, lens and deflector. Resolution about 20 nanometer is possible. The disadvantage of the method is that it has to written individually, so it is slow process. Also, it requires a higher vacuum, about 10 to power minus 6 torr, and so the process is slow and expensive. Now, how the mask aligner system will look like, we have a recorded video, but these are also some of the mask aligner in our center facility. This is EVG 620, and you can see how the wafer, here the wafer can be loaded, and here the mask can be loaded, and you have a bright field microscope, you have split field microscopy where you can see the alignment mark simultaneously. This is another one which is MJB4. Here this is a stage for aligning the wafer and the mask, and we will see an example of how the mask and wafer are aligned, so to expose the wafer and get the features desired features from the mask onto the wafer. We will also see the role of alignment mark as taking an example of a pressure sensor. So, till then I think this is the last slide for our lithography section. I hope that you, even it was little bit faster, I hope that you understand that lithography is a technique by which you can pattern different kind of materials. Now, in the next class when I will teach about how to use this lithography, how to use the physical deposition technique and combining need to fabricate few devices, it will be further cleared. Alright. So, till then you look at these slides, look at the lecture notes. If you have any question, you feel free to ask us on NPTEL forum. Till then, take care, bye for now.